In this video, we're going to look at direct comparison and limit comparison tests for infinite series. First, let's start off with the statement that we're going to let A sub n be a series that's less than or equal to B sub n. We're going to have one series given in our problem. We're going to find a very comparable series to compare it to that we know either diverges or converges. A couple of recent series that we've looked at are geometric and p-series. Geometric series will converge if the ratio or r value is less than 1. A p-series will converge if its power in the denominator is greater than 1. So we're going to use series that we know, even just by visual inspection, either diverge or converge, and we're going to compare those to the series given in our problem. Ultimately, what these two statements mean is if the larger series converges, then the smaller series must also converge. Number 2, if the smaller series diverges, then the larger series must also diverge. So if we can get a larger one to converge, the smaller one will too. If we can get a smaller series to diverge, then the one larger than it will also diverge. Our first example, we have the sum from 1 to infinity of 1 over 2 plus 3 to the n. This is very much like 1 over 3 to the n. If you just ignore the plus 2, sort of look at your dominant terms. This is very comparable. And this is a geometric series. Think of it as this way. 1/3 to the n. That ratio is less than 1. So we know that this one converges. Let's investigate what happens between the original and this one we're comparing to. Okay, so that's the original versus the comparison series. The left fraction will have a smaller value because its denominator is slightly larger. If we're going to take 3 to the n and add 2, that's going to be more than just 3 to the n, creating a smaller value overall. Now 1 over 3 to the n, from the blue ink, we could write that as a geometric series. Its ratio is less than 1, so it's a convergent. And remember from the two statements on the first slide, if the larger one converges, the smaller one must also converge. And it's as simple and also as difficult as that. You find a simpler series that you know converges or diverges, compare it to the original, and so this infinite series will converge. This next example, the sum from 1 to infinity of 1 over 2 plus square root of n, again, focusing on the dominant terms, we could compare this one to one over square root of n. Basically, you want to compare it to the most dominant terms from the original series. This can be rewritten as 1 over n to the half. that value is less than 1. So what does that tell us? Not much. The problem is, this is a divergent series, the one that is comparing in blue. The problem is, it's larger than the original, so that doesn't meet the right stipulation that we're creating a comparison series that's greater than the original. That only works if the greater one converges, then the smaller one converges. We've built one that's a larger series in blue, but it's divergent. So that tells us nothing. Okay, now I'm not going to erase that. I'm going to exit out. We got to go back to the drawing board. And these are some thought processes that you'll undergo. Let me try another one. Let's look at the Harmonic Series. Now, if you want to play around with a few values, that's totally fine. Like plug in a 1, then plug in a 2, compare your values. It turns out that once you get to 4 or larger, that 1 over n is smaller than 1 over 2 plus square root of n. One over n has an unwritten power of 1, and by p-series, that's divergent. Now the good news is we have found a smaller divergent series, and that means anything larger. And it's okay if you have to count up to 3 or 4 to establish dominance where one series is greater than the other. They're going to infinity, so even if it takes a few finite values to make that happen, that's totally fine. But part 2 of our direct comparison test, and that's back from the first slide, if you can get a smaller series to diverge, a larger one must diverge as well. A smaller one diverging means a larger one will diverge also. A larger one converging means the smaller one converges. And that was our first example. This example is part 2 of the direct comparison test. Limit comparison is very similar in stature. You're going to have a series given. You're going to create a very similar series based on dominant terms from the original, but you're going to set up a ratio of AN over BN and look at the limit of those two when n gets really large. If your limit comes out to a positive finite value, then either both, original and the one you create, will converge, or they will both diverge. So it's similar in that nature, where you have either both convergent or both divergent. You just have to be careful when you set this up. Okay, so we've got the series from 1 to infinity of square root of n over n squared plus 1. If you look at the dominant terms from this original series, you have square root of n over n squared. Which is 1 over 3 halves as your power. Now that power is greater than 1. This is a convergent, and we know it converges by p-series. Using limit comparison test, we're going to compare the original to the one we built. Which is going to give us the limit as n approaches infinity of, and that's a complex fraction, so I'm just going to copy the top times the bottom one flipped over multiply the numerators together, the denominators together. That gives us limit as n goes to infinity. Square root of n, that's n to the half, times n to the 3 halves. When you add those powers, a half and 3 halves makes 2. N squared plus 1 times 1, that stays n squared plus 1. And when you dial up the x values really large, we're going to get a limit of 1, which is positive and finite. Since this one converged, the one we built, the original must converge as well. Our next example, the sum from 1 to infinity of 6 to the n plus 1 over 7 to the n plus 1 is very comparable to the series, and it's, again, 1 to infinity. Main thing is just building a very comparable one. 6 to the n over 7 to the n, which can be rewritten. Let's see, let me do a little bit better job of that. Of 6/7 to the n. Now, since that's a geometric series with a ratio less than 1, the one we've built is convergent. Limit comparison says it's okay, and it fits the bill for limit comparison test, is we could do limit as n goes to infinity, original over the one we built And like the last example, this is a complex fraction. We can take top divided by bottom is the same as top times the bottom flipped over. As n gets really large, these plus ones won't count that much as far as the value. they kind of become insignificant. If you concentrate on the original series without the plus ones, and you're multiplying it times the reciprocal of the one you built, you get cancellations all around, don't you? This limit comes out to 1, which is finite and positive. Since the one we built converges, the original will too.